We're going to continue looking at how to solve trig equations with this example number 5. We want to solve 3 secant squared x minus 2 tangent squared x minus 4 equals 0. Now the problem with this equation is they're not all the same thing. We have secants and tangents in the problem, which is going to make it very difficult to solve. So what we want to do is use one of our trig identities to make a substitution. So I am going to replace secant squared using my second Pythagorean identity. So remember that was the 1 plus tangent squared x equals secant squared x. So I'm going to replace the secant squared x with 1 plus tangent squared. So this equation becomes 3, 1 plus oh, that was not right. Hang on. 1 plus tangent squared x minus 2 tangent squared x minus 4 equals 0. So just using that Pythagorean identity, we'll get everything in terms of tangent. I'm going to erase this because I need lots of room. All right, so then I'm going to distribute the 3 and combine my like terms. And so when I do that, I get tangent squared x and minus 1 equals 0, which will give me tangent squared x equals 1. I'm going to take the square root of both sides. And remember, I'm introducing the square root, so that means tangent x is plus or minus 1. So now it's time for me to draw the triangles. So we're thinking that all students take classes. And it's plus or minus, so we could be in any of the quadrants. So let's go ahead and draw it in all of them. So we know that tangent is 1, so that's opposite, and adjacent is 1. So clearly this is a 45-degree angle. So one of my solutions is going to be pi over 4. Now, it's going to be another 45-degree angle over here, so my other solution is 3 pi over 4 and 5 pi over 4 and 7 pi over 4. Now, this is only going to happen with the tangents, but notice that every time I go a quarter way around the circle, I hit another solution. So a shortcut for writing the answers to this will be pi over 2n, because every time I go 90 degrees, I hit another solution. That only happens when it's a 45-degree angle. Okay. Now, if you had instead said, look, my answers are, pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4, and then plus 2 pi n, this is also correct. It's just kind of the long way to do it. But it still does the same thing. It shows, look, all 4 quadrants have a triangle, then plus every time around the circle. The way I did it in the circled answer is just the shortcut. Now, sometimes when we're solving problems, we may want to square both sides of the equation, which is an okay thing to do, but it may produce extraneous solutions. So if you ever find yourself squaring both sides of the equation, check your answers. And we're going to see that here in number 6. Now, the good news about number 6 is, notice it says on the interval 0 to 2 pi, so we do not have to worry about that plus 2 pi n thing. Okay, we're just going to find the solutions one time around the circle. Okay, so going back to our equation, we have sine x plus 1 equals cosine x. We have a similar problem to the last equation, that we have sines and cosines, and we can't solve it having 2 different things. So I'd like to use one of my Pythagorean identities to make a substitution, but remember the only Pythagorean identity that I have is sine squared plus cosine squared, and neither of these are squared. So I can solve that by squaring both sides of the equation. So that's what I'm going to do. So I'm going to square this, I'm going to square this. So that's going to give me sine x plus 1 times sine x plus 1. And then this side will give me cosine squared x. And that's the whole purpose, because now I can use this Pythagorean identity to replace cosine squared with 1 minus sine squared. So now everything's going to be in terms of sine, which is good. I still have some more work to do because I need to FOIL the left-hand side. So this is going to give me sine squared plus 2 sine x plus 1. And then I'm going to move everything over to the left side. So it'll give me 2 sine squared x plus 2 sine x, the ones cancel each other out, equals 0. Okay, I do want to factor this, so I'm going to factor it by taking out a GCF, which is 2 sine x, which leaves me with sine x plus 1. And then I'm just going to erase that because I don't need it anymore. I'm going to set both of these equal to 0. So either 2 sine x equals 0 or sine x plus 1 equals 0. Just my two factors. We divide both sides by 2. So either sine x equals 0 or sine x equals -1. Okay, so now we want to think about where the sine is equal to 0. We can draw triangles on this, but actually what I'd rather do is think about the unit circle. Okay, remember sine is the y-coordinate. So the y-coordinate is 0 here and here. So at 0 and at pi. And then over here, I'm going to do the same thing. I'm going to think about the unit circle. Remember, sine is the y-coordinate. And I want to know where the y-coordinate's -1, and that's the only place it's going to happen. So 3 pi over 2. So these are my three solutions. Now remember, back at the very beginning, I squared both sides of the equation. Okay, so I have to go back to this original equation without the squares. I have to go back and make sure that these actually work. Okay, so let's try that. So first I'm going to plug in 0. So I want to know, is the sine of 0 plus 1 equal to the cosine of 0? Sine of 0 is 0. Cosine of 0 is 1. So that one does work. All right, and then I'm going to plug in pi. So is the sine of pi plus 1 equal to the cosine of pi? So sine at pi is 0. Cosine of pi is -1. So that doesn't actually work. So we don't get that one. And then I'm going to plug in 3 pi over 2. So I want to know, is the sine of 3 pi over 2 plus 1 equal to the cosine of 3 pi over 2? Sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0. So that one does work. Okay. So my final solutions are just 0 and 3 pi over 2. Pi was an extraneous solution, so we had to throw it out. So anytime you happen to square both sides, make sure you plug in your answers and make sure they all work.